Here we discuss about the reproductive property of normal distribution. Now we know first what is reproductive property of normal distribution, and it says that if x1, x2 to xn are mutually independent, this is very important term, mutually independent normal mi comma sigma I. Okay, that is x1 is normal m1 sigma 1, x2 is normal m2 sigma 2, and so on, since I equal to 1 to n. Then the random variable which is given by the linear combination of a1 a2 an, which is given by a1 x1 plus a2 x2 to an xn, and this is denoted by sn, where ai are real number for I equal to 1 to n, is also a normal m sigma distribution. This is the reproductive property. The linear combination of n independent normal distribution is also a normal distribution. But here the mean and standard deviation of this Sn or normal distribution is given by a1 m1 plus a2 m2 to an mn, and standard deviation is root under a1 square sigma 1 square plus a2 square sigma 2 square to an square sigma 1 square. Okay. Here we first find out the characteristic function or moment generating function, any one of them, of normal distribution, and for which we have to require the PDF of normal m sigma distribution. And we know that the characteristic function, this is the solution, characteristic function phi xt, if we let x as a variable first, and this is defined as integration minus infinity to infinity. We first write the definition. This is expectation e to the power I tx. There, this is the characteristic function. And for normal distribution, we write this is minus infinity to infinity e to the power I tx into fx. This means 1 by root 2 pi sigma e to the power minus half into x minus m by sigma whole square dx. Okay. Now we integrate this term as this is 1 by root 2 pi sigma minus infinity to infinity, and if we add this 2 exponential, we get the result as this is e to the power minus half into x minus m whole square minus, since we take common minus half here, this is minus 2i, this is minus 2i tx sigma square, and into dx is here. Okay. Now this is written as 1 by root 2 pi sigma into integration minus infinity to infinity e to the power minus half into, if we expand this, we first write x square term, then we get x into, and we first write 2x into, because 2x is here, from here we get the result 2mx, so we write here 2x into m, and from here we get this is plus it sigma square. Okay, and to make it perfect square, we add here this is m plus it sigma square whole square, and here a term present which is given by plus m square minus, to balance it we subtract again this term, this is m plus it sigma square whole square, and this is by sigma square we write here, and this is dx. This is the complete integration. Okay, so we write 1 by root 2 pi sigma into integration minus infinity to infinity e to the power 1 by 2 sigma square into, this is given by x minus m plus it sigma square whole square, from first 3 term, and from last 2 term we again write e to the power minus 1 by 2 sigma square, and from this we get minus, this is 2it m sigma square plus, this is also minus because here I square present, and this is given by m square cancel out. This is again plus, because I square is again minus. Okay, so 2 minus and 1 plus, this is plus. This is given by t square sigma to the power 4, and dx is also present here. Okay, now since this term is completely constant with respect to x, okay, because the integration is respect to x, so we write it outside of integration, and we get the result as e to the power minus this 2 and this sigma square we write inside the bracket, and sigma square cancel out. We get this is e to the power minus t square sigma square by 2. From here we get plus sigma square cancel out, 2 cancel out. This is plus imt. Okay, imt plus minus t square sigma square by 2 we get, and another term or remaining term 1 by root 2 pi sigma. This is minus infinity to infinity, and this is given by e to the power minus half into x minus m plus it sigma square, and this is square by sigma, and again this is square. Here is dx, we write here dx. Okay, now since this integration is look like this, this is minus infinity to infinity 1 by root 2 pi sigma e to the power minus half into x minus mu by sigma whole square dx. Clearly this is normal mu sigma distribution, so the integrating value is 1. So we put directly this value is equal to 1, so we get the characteristic function of normal m sigma distribution. This is e to the power imt minus t square sigma square by 2. Okay, this is the characteristic function of x, where x is normal 0 1. So we write phi xt. This is given by e to the power imt minus t square sigma square by 2. Now since x1, x2, xn are mutually independent, and here the variable is sn, so we write phi sn t. This is the characteristic function of the variable sn, and which is given by, in definition, if we put sn in place of x, we get the result expectation e to the power I t sn. Okay, and then expectation e to the power I t. This is sn. Sn means we put this value. This is a1 x1 plus a2 x2 to an xn. Okay, and since x1, x2, xn are mutually independent, we repeatedly says that this term is very important. So we can write this expectation as the product of expectation e to the power I t x1, a1 x1 into expectation e to the power I t a2 x2 to expectation e to the power I t an xn. Okay, now if we put the value of this expectation, that is this is the characteristic function of x1. Here the real variable is taken to be t a1. Okay, so we directly write from here, we get that this is given by e to the power I into m. M is given by m1. We says that this is m1 because the mean of x1, this is m1, and we write a1t in place of t because here the real variable is a1t, and this is the first term, and the second term is minus t square. So we get a1t whole square into sigma square. Sigma square means sigma 1 square. Sigma 1 square by 2. This is the first value, and in similar manner we put the last value also, and we get e to the power I into mn ant minus ant whole square into sigma n square by 2. Okay, and then we divide here, then we add all the exponential term, we get the result as exponential of I into, this is given by m1 a1 plus a2 m2 to an mn, right? And from the second term, this and this, we get half into, this is given by half into, we write first t square by 2 because this is t square by 2 into sigma square. So we write here in the bracket a1 square sigma 1 square plus and so on an square sigma n square. Okay, and clearly this is nothing but similar as the characteristic function of normal distribution, but here two changes are, which in the first term, this is in the term of m and in the term of sigma square. Okay, so we write that this is we write that this is characteristic function of normal. We write m is this normal m1 a1 plus m2 a2, or we write in the form as, since it is given in our problem that a1 m1 plus a2 m2 to an mn. Okay, and sigma is given by root of this, so this is a1 square sigma 1 square to an square sigma 1 square. Okay, and from here, using the given result, we write this is nothing but this is n of m sigma, where m is this and sigma is this. Now here we use the uniqueness theorem of moment generating function or characteristic function, and in simple word, this theorem states that, this uniqueness theorem states that if for two variables x and y, the moment generating function or characteristic function of x and y are same, then we say that x and y are the same distribution. Okay, so from this result we say that Sn, this is the linear combination of x1 x2 xn, is also a normal distribution whose mean is m, which is given by this, okay, and whose standard deviation is given by sigma, which is given by this, and we prove our reproductive property of normal distribution. This is very, very important property, and we say it is very, very important theorem. This theorem helps us to solve so many problems of normal distribution using this and these two formulas. Okay, thank you for watching.